right, 3.1 is exponential functions and their graphs. So chapter 3 is exponential functions and logs, stuff like that. I'm sure you think of fondly. This goes back to part calculator, part not calculator again. So if you've got it with you today, you're going to need it. If you don't, you want to start bringing it with you. So the graphing part won't really probably be on the calculator. The part dealing with exponential functions that are not possible to find without would be. So we start with the definition of an exponential function and the parts of it. So this is something that is obviously a base raised to a power. The base is the big number. So in this little f of x equals a to the x example, the a is the base, the x is the exponent. The a will be greater than 0, or sorry, if the a is greater than 0, you could have a negative on the front of it, okay? But you'll see that written differently, like a -2 times something raised to the power kind of a thing. And the base won't be 1, because what happens if I raise 1 to the 3rd power? What if it's 1 to the 10th power? So what kind of graph would that look like? Linear, more specifically? Constant, right? Never changes. Does that make sense? So it would be a straight line. These are going to be exponential, which means they are going to be increasing or decreasing depending on what the base is. So the first thing we're going to do is literally just evaluate. So this is what you need a calculator for. Okay? You're going to be careful paying attention to directions on the rounding and like how many, and then also being careful on your part on the rounding itself. So it says evaluate the function of the indicated value of x and round your answer to 3 decimal places. So in your calculator, most of you will be taking that 0.5 and then the little caret and then 1.2. And you should get 0.435. 2 would be the next number, and you're going to drop it off because you're rounding. And then 150 times 2 to the -0.25, or -2.5. And you should get 26.5165, which becomes 517. If you get scientific. All right, so the graphs of these exponential functions, okay, have all these characteristics. So the domain of them is going to be all real numbers because you're moving from left to right. There's no stops in these graphs. There's no holes in these graphs, okay? The range is going to be the lowest point, obviously, to positive infinity. Now, for the parent function, you have a horizontal asymptote at 0 because if your base is positive, there's no way for you to raise it to a power that would make it negative. Nor is there a way for it to be 0. Is there any number I could raise a power to get it to be 0? No, right? So you'll have an asymptote at y equals 0, unless, of course, there's a shift, which we'll talk about in a little bit. So your range is going to be, in this case, it would be 0 to positive infinity, and there's going to be a parentheses on the 0 because you're not including 0. Number 2 says the graphs of all exponential functions are in the form of f of x equals b to the x passed through point 0,1. So again, this would be for a parent function. What happens when I plug a 0 into an exponent? Anything raised to the 0 power is what? 1. So without a shift, that parent function is always going to pass through 0,1. And then 3 says if b is greater than 1, so if your exponent is positive, then it has a graph that is increasing as you move from left to right. And the higher the value of b, the higher the steeper the incline. If the exponent is in between 0 and 1, like a half or a third or something like that, then it has a graph that's going to decrease as you move from left to right. And then it's 1 to 1 because it would pass your horizontal line test, which means it has an inverse. We're going to learn about those in a little bit when we start talking about logs next week. And the graph approaches but does not touch the x-axis. So that's what we were talking about before. There's no way for these functions to be 0. So they will approach but not touch that x-axis. All right, so we're going to graph these. And we're going to graph by plotting points. So these you would do without a calculator. So I would just set up a t-chart and start with the same 3 points that we plug in. So if I raise 3 to the negative 1, I get what? 1/3. So a negative exponent brings that number down to the fraction, or to the bottom part of the fraction, right? How about 3 to the 0? 1. How about 3 to the first? 3. And now I'm going to graph these. So negative 1 and 1/3, 0 and 1, and 1, 3. So this is increasing as you move from left to right. What would the domain of this function be? All real numbers, negative infinity to positive infinity. How about the range? That's not the lowest point, right? It's going to keep getting littler and littler and littler and littler. So how do we write that? Good. So you're going to have a 0 with a parentheses on it because you're saying it's getting as close to 0 without touching 0 to positive infinity. So domain would be negative infinity to positive infinity. And range would be 0, but it has to have a parentheses to positive infinity. Which part? The domain or the range? So the range, like think about what's happening here. There's the horizontal asymptote here. So that it won't touch. It's never going to actually touch 0. But the further left I go, the closer it gets to 0, which means I could have like a 0.9999 or 0.00000000001 on that graph. I just can't have a 0. So instead, there's no way to write that other than saying it's going to be 0. It starts exactly after 0, which is 0 with a parentheses on it.
Is it always going to be that?
No, if there's a vertical shift, which we'll do a couple. We'll do the vertical shift, then it shifts that. All right, now let's go to B. So same 3 points. I'm going to plug in negative 1, 0, and 1. And I get 3 to the negative 1, which becomes what? Good. 3 to the first or 3. God bless you. And then 3 to the negative 0 is still just 3 to the 0, which would be 1. And 3 to the negative 1, which would be 1/3. Now negative 1 and 3. 0 and 1, and 1 and 1/3. And domain and range are the same. They're both negative infinity to positive infinity. And the range is 0 to positive infinity. All right, so the yellow and the green one should be your 1/4 to the x power. If I plug in negative 1, I get 4, 0, I get 1, and 1, I get 1/4. That's the green one. And then the blue one, plug in negative 1, you get 1/4, 0, 1, and 1/4. And then I said to draw the asymptote. So the asymptote is down here at y equals 0. Okay, again, it's going to get as close to that line as it can without actually touching it. Questions on that? The asymptote would be at y equals 0, yeah.
Will it always be?
No, if there's a vertical shift, it's going to shift with it. Which is this, right? So all the translations that we have done with parabolas and square roots and cubic function, all the other stuff, apply to these as well. So if I have an addition or subtraction after the function, this is going to be a vertical shift. If you have it in the exponent with the variable, it's going to be a horizontal shift. Same thing as usual. If it's plus, it goes left. If it's minus, it goes right. If it's in front, if you have a negative on the base, it's going to be reflected over the x-axis, okay, or flips it upside down. If you have a negative in the exponent, it flips it over the y-axis, so like left to right. And then you've got vertical stretching or shrinking. If there's a number in front of the base, like it said 2 times 3 to the power of x, then that would be a vertical stretch as though you were pulling it from the top and the bottom. If it was a fraction there, less than 1, then it would be a shrink, like the ceiling and the floor is caving in on the function. And then there's a horizontal stretching or shrinking. So if there was a number being multiplied by the exponent here, it's causing a horizontal stretch or shrink. And it's kind of the opposite that you would think. If it's bigger than 1, it actually shrinks the graph as though the walls are caving in on it, which makes it taller, kind of, like makes it go up faster. And if it's a fraction, then it actually elongates it. So as though you took the left and the right sides and you stretched it out. So take what we know of 4 to the x. So we just did this one. 4 to the x would have been 1/4, 1 and 4. This is my original function. That's my f of x. And now translate it. What would happen if I said plus 3 after the function was done? Good. It's a vertical shift up 3. So every single point goes up 1, 2, 3 places. So that's 3, 1, 2, 3. That's 3. And this 4 would be up 1, 2, 3, all the way up the top. So where my asymptote was here before, it's now here at y equals 3.
So the range would be 3 to...
Exactly. So your domain doesn't change, but the range on this one would now be 3 to positive infinity. The points, just shift every single one of the ones you had up 3 places. Yep. So if the x minus 2 is in the exponent, what happens? To the right 2 places. So if my initial point was here, it's now 1, 2 here. Nope. 1, 2 here. If my point was here, it's now here. And if my other point was here, it's now here. And my graph would look like that. Does the domain or the range change? No. Both negative infinity to positive infinity for domain, and both 0 to positive infinity for range. Sophia.
Wait, so the range for, the domain for the last one would have, the range. The domain's always negative infinity to positive infinity.
For every exponential function.
But then for the last one, the range would have been 3.
The one. All right, this is a property you're going to hear a lot for the next chapter. It's called the one-to-one property. So the one-to-one property just says that if a to the x, in order for a to the x to equal a to the y, the bases and the exponents have to be the same. So when you're writing 2 exponents or 2 exponential expressions, the goal is to change them so both the bases are the same. And if both the bases are the same, then you can set the exponents equal to each other. Okay, and then also, we already talked about it, but remember that anything raised to the power of 0 is 1. There is no way to figure that out. It's not like you can multiply something by itself 0 times to see what it is, right? You can't do that. It's straight memorization. And it's something people make easy mistakes on. So just be careful. So that will look like this. It says solve using the one-to-one property. So my goal with these, again, is to make the bases the same. So I don't ever want to change the smaller one. I want to change the bigger one so that it's written in terms of the smaller one, okay? So I want to say, how can I change 9 so that it is written in terms of 3? And it would be what? 3 to the second. And then once the bases are the same, so these are the same, I can actually ignore them and just set the exponents equal to each other. So I get x minus 2 equals 2. And add the 2, and I get x equals 4. Yep. These are really easy to check. If I take this 4 and I plug it back in, 3 to the 4 minus 2 becomes 3 to the second, and 3 to the second is 9. So I know it's right. Okay, B, and I'll tell you right now there's a couple ways to do this. So it all depends on which way your brain sees it. I can either make them both the same whole number base. So I could take 1/2 and make it 2 by doing what? Think about it in terms of a power. How would I make 1/2 2 to the something power? It would be 2 to the negative 1. Everybody understand that? So I can rewrite this as 2 to the negative 1 raised to the x, which becomes 2 to the negative x. And then I can change 16 to be 2 to the what? 2 to the 4th. And then because the bases are the same, I set the exponents equal to each other. And I get x is equal to -4. The other way to do it is bring 16 to the bottom. So I can say that 16, 1 over 16 to the -1, and then 16 would become 2 to the 4th, so this would be 1 over 2 to the -4th, and then you set your exponents equal to each other. So whichever way your brain sees it, stick to it, okay? There's a lot of different ways, especially when we get into logs and stuff. There's a lot of different ways to do these. Ian?
Can you explain how you got from -1 to -4? So the second method?
So this, rewritten as 2 in the numerator, is 2 to the -1.
Mm-hmm.
And then there's an x there. So I did -1 times x, and that would have been 2 to the -x.
Okay.
And then the right-hand side, I took 16 and rewrote it as 2 to the power of 4. Because 16, so, and there's gonna be sometimes where it's obvious and someone it's not. So like if I broke that down, you would see there's 1, 2, 3, 4 2s. And that's how I can rewrite 16.
Got it.
And then again, you can check it, right? So if I take this and I plug it in up here, the negative brings the 2 to the top, and then I'd get 2 to the 4th, which is 16. The last one, like I said before, straight memorization. What do I raise 6 to make it 1? 0. There's no other way to do it. Well, there is, but it's worse. So just go with this one. X equals 0. Right, the natural base. So E is a variable that represents a value that is 2.718281828, and so on and so forth. This is an irrational number, so it doesn't end. And it's referred to as the natural base. When you put it in a function, it's called the natural exponential function. Eventually, we're going to deal with it in logs, and then it becomes the natural log. So your calculator has a button, probably the ln button, and above the ln button is your e to the x. You're going to need that one. It's kind of like pi, right? Pi represents a number that's irrational, doesn't end, doesn't repeat. E is the same thing. We approximate E to be, and this is on this next one. So this is a big, long explanation about where E comes from, to be honest. All you need to know on this one is that E is approximately 2.72. The rest of it confuses people more than it helps them. All right, so it says use a calculator. Example 7 says use a calculator to evaluate the function f of x equals x, or e to the x, for each value of x, and then round it to 3 decimal places. So again, graph and calculator, find your ln button. Above your ln is your e to the x. And e to the 4.2 is 66.6863, so 686. And then the next one, 125 times e to the 0.05 times 30. Make sure that 30 is in the exponent. And you should get 560.211. Okay, so this time it says to use a graphing utility to construct the table of values. So notice it's not asking you to use the graphing calculator to graph it. You're just using it to find the values. Okay, so if I plug in the same 3 values, -1, 0, and 1, and you can simplify it first if you want to, but your calculator can also do that work for you. So if I did 4e to the -1 plus 2, which is 4e to the first, I get 10.87, so I'm going to round that to 10.9. 4e to the second, and I get 29.5, so 29.6. And then 4e to the fourth, and I get This should be 2, so it's 4e to the third, which is 80.3. And then I'll adjust the x-axis, so let's make it like 20, or the y-axis, 40, 60, 80. So -1 and 10.9 would be about here. 0 and 29.6 about here. And 1 and 80.3 about there. So be careful when you're graphing these because you don't get the full loop at the bottom. But because you know that an exponential function should approach the y-axis, you need to make sure you extend that graph so that it does that. So unless there's a vertical shift, which there's not here, it should look like your regular exponential function. All right, this is compound interest. So there's 2 ways to compound interest. One is a certain number times a year, which is what number 1's formula says. The second is continuous. So this is happening faster than like the human brain can even attempt, which is where the natural base comes into play. Okay, I'll often refer to that as the PERT formula because it's P times E to the RT. And then the first one is compounding either daily or weekly or monthly or semi-annually or annually, okay? Where N represents the number of times per year it's compounded. So if I said something was being compounded annually, what is N? 1. If I said it's being compounded monthly, 12. Weekly, 52. Good, that's something you need to know. 52 weeks in a year. How about daily? 365, okay? Bi-monthly means what? Twice a month. Biannually, twice a year. Okay, so those are the things you have to know, okay? So if I said bi-monthly, what would be my N? 24. Does that make sense? Okay. The one on the bottom doesn't need an N because it's constantly being compounded. The R stands for the rate. It's going to be given to you in percent. You're going to have to get it into decimal form. And then the T is the number of years that money is in the account or whatever it is. And P is the principal balance. A is what would happen at the end, okay? So if I put $1,000 in and it's earning 5% and I'm getting compounded a monthly, then you would take each of those parts and plug it in. The more you can compound something, the more earnings you're going to get on it. So if this is like a savings account and it says you're going to compound it once a year or continuously is better because it's constantly compounding, which means, let's say I started with $10 and it's 5%. What's 5% of $10? Let's try this easier. What's 10% of $10? $1. So let's say I'm compounding $10 at $1 every day, right? So at today I started with $10. What's my balance tomorrow? $11. Now I'm earning 10% off $11. So then I'm getting what? Oh, so close. What's 10% off 11? Move your decimal one place. 1.1. So now it's $12.10. You see me? Yeah? You getting this? So that's every day, not like literally see me. You get it? Yeah. Okay. That's compounded daily. So every time it compounds, it's better for you, unless this is a credit card and then it's worse, okay? Because it's working the opposite direction. So the more times it's compounded, the more earning, which means if you are comparing answers and I had A, monthly, B, daily, C, continuously should be the most. Daily would come next, and then monthly would come the smallest if you're comparing them. All right, so this says find the accumulated value of an investment of $15,000 for 2 years at an interest rate of 3.2% if the money is, and there's 4 different ways it's compounded. So let's start with the given information. I have 2 equations. A equals P times 1 plus R over N to the NT. These you got to memorize. And A equals P times E to the RT. PERT, yep. So what is P? 15,000. For 2 years, what does that represent? This is your T. At an interest rate of 3.2%, what is that? R. And that's in percent, which means what in decimal form? Good. 0.032. So you're going to move your decimal 2 places to the left. All right. So what would N be if it's compounded semi-annually? 2. What would N be if it's compounded quarterly? 4 times a year. How about monthly? 12. And continuously, there is no N. You use PERT. So plug them in. 15,000 times 1 plus 0.032 over, the first one is 2, to the 2 times 2. And then the next one would be 15,000, 1 plus 0.032. This time it's compounded quarterly, so 4 times 2. And then 15,000, 1 plus 0.032 over, this time it's 12. 12 times 2. And then the last one is 15,000 times e to the 0.032 times 2. And then let the calculator do the work. Be careful how you type this in. So it should be 1,500, or 15,000, sorry. Open your parentheses. 1 plus, open your parentheses again, 0.032 divided by 2. Close your parentheses, close them again. And then raise to either the 2 times 2, or you could actually do that math and make it 4. So this is how you want to enter it into your calculator. Again, make sure you're careful with the parentheses, because one little mess up and that number comes out wrong. Hopefully it makes sense. If you think about the fact that you started with $15,000, you're only earning 3.2%, and you're only keeping it in there for 2 years, your number should not be astronomical, okay? So this is $15,983, and we're talking about money, so we're going to round it to cents, which is 29 cents. That's the first one. And then if you don't know how to do this, learn, because it will save your life. If you arrow up on your calculator to the point that you actually click on
Slight interruption. Carlos Ramos, please report to student services. Carlos Ramos, please report to student services.
Okay, so if you arrow up on your calculator, if you hit the arrow up and you hit enter, it's going to duplicate that line for you. And then all I have to do is change what's changed. And then the next one, it's the bottom of the fraction inside. This would be 4. And then on the outside, one of those 2's becomes a 4. And then hit enter again, and you get your next one. So that would be $15,987.31. And then I would do it again, arrow up. This time the bottom is 12. And it'd be 12 times 2 in my exponent. And then the last one is 15,000 times e to the 0.032 times 2. And this one is $15,991.39. And again, it should make sense that the more you compound it, the more money you're going to get. So that last one should be bigger than all the others.